is a little bit laggy. The audio should still be on there. All the information should still be there, but it looks like my computer's having trouble. Maybe it needs a video card update or something. Let's talk about these intermolecular forces. Right, so the first category we talked about, we started by talking about ionic bonds, right? Because what causes an ionic bond? What is it that makes ionic compounds stick together? Electrons, kind of. My friend in undergrad used to joke that if you ask a why question about anything in chemistry, you can just answer electrons, and you're not technically wrong, because basically electrons cause pretty much everything in chemistry to happen. That was a great joke, a real knee slapper. But more specifically, what about electrons is causing ionic compounds? Gains or loses, that's what makes something an ionic compound, is when you have something with a positive charge and something with a negative charge. Because what do? They stick together, right? So our strongest form of bonding is basically just when you have something with a positive charge, something with a negative charge, they're going to tend to stick together. So the way that all of these other forces, all these intermolecular forces work is always going to be partial positives or positives and negatives being attracted to each other. Right? So the strongest form of intermolecular forces actually involves ions as well. These ion dipole bonds are the strongest type of intermolecular force. Because if you have polar molecules, they're going to be attracted to ions as well. The force of attraction between two charges, and again, it's been a while since I took chemistry, but I want to say it's charge 1 times charge 2 times a constant over the radius squared.
Yeah, Coulomb's law.
Coulomb's law, yeah. There's a constant involved in here too, probably Coulomb's constant.
Yeah.
But what this is really saying is that the bigger your charges are, the bigger the attractive force, which kind of makes sense. If we had, say, calcium and sulfate, those are going to have a lot stronger attractive force than sodium with a +1 and chloride with a -1. Right? Bigger forces mean stronger attraction. So similarly, like you have different strengths of magnets you put on your refrigerator ohm, right? Usually if you're buying cheap magnets, are the ones that barely stick. You put one piece of paper underneath them and they fall off. But you can also have really, really strong magnets. The stronger the charge between these two, the stronger they're going to stick together. Right? So an ion dipole force would be like if we surrounded, we'll just use the calcium here. If we surrounded a calcium ion with a whole bunch of water molecules, right? What part of the water molecule is going to stick to a calcium ion? What does a water molecule look like in terms of its charge? The oxygens have that partial negative, right? And the other side of the molecule has a partial positive. Oxygen's more electronegative than hydrogen, so it's pulling all the electrons towards itself. So if you put calcium ions and dissolve them in water, they're all going to arrange themselves so that you have all these water molecules with the oxygen pointed towards the calcium. They're all just going to arrange themselves that way. And that's going to be a pretty strong intermolecular force because there's a pretty strong partial negative on this oxygen, and there's a full +2 charge here on the calcium. So these ion dipole forces are what we get anytime we have an ionic compound dissolved in anything, basically. The whole reason that an ionic compound will even dissolve in water in the first place is because we get to make a whole bunch of these really favorable interactions. it may not have occurred to you yet, but, and I kind of already gave the answer away, but if you have an ionic compound that dissolves in water, it's because we get to make these favorable interactions. Otherwise, these ionic compounds would just stay in their crystal form, right? Because if the ionic bonds are so much stronger than these intermolecular forces, why not just stay as that crystal structure? And the answer is because we get to make more of them sometimes. Not every ionic compound dissolves. What do we call it when we mix an ionic reaction happening where you mix two solutions and then they stick together to form a solid? Who remembers that type of reaction? Precipitation, right? So not every ionic compound will dissolve in water. But if they do dissolve, it's because we get to make these favorable interactions. Mostly. Would we expect something with a really positive charge if we are looking at ionic compounds? We had something like NaCl versus calcium sulfate versus aluminum phosphate. Which of these would we expect to dissolve best in water? Could we generalize about that yet without your solubility rules? What's different about these ionic compounds? Everything. Not everything. Two of them have oxygen. This is a +1 and this is a -1, right? What are your charges on calcium and sulfate? +2, -2. What about aluminum? +3. And phosphate's a -3. Which of these would you expect to dissolve best in water? Which one is being held together the least? That's a much weaker ionic bond because the charges are lower. Then calcium sulfate might dissolve, but not particularly well. And aluminum phosphate, I can pretty much guarantee you that's not going to dissolve without even looking at solubility rules. The stronger these charges, the more they're going to stick together. Right? And that the rest of this slide follows that same logic. The strongest intermolecular forces are ion dipole forces. And then all of these other three are all just different versions of dipole-dipole interactions. Right? So hydrogen bonds, we specifically said if you have a polar molecule that involves hydrogen forming a covalent bond with what? What makes something a hydrogen bond or able to have hydrogen bonds? It's on the slide. Hydrogen bonded to fluorine, oxygen, nitrogen. I put chlorine in that category as well because chlorine is about the same electronegativity as nitrogen. Anytime you have a polar molecule that involves hydrogen in a covalent bond with any of those four, the four most electronegative elements. So, for instance, if we had a molecule like methanol that has a Lewis dot structure that looks like this. We haven't done too much practice with Lewis dot structures where you've got two central atoms yet. But if I give you this structure, we can see that we have a hydrogen attached to an oxygen. Our least electronegative nonmetal that doesn't have any core electrons in a covalent bond with one of the most electronegative elements. So anytime we've got a compound with that feature, with a hydrogen directly attached to oxygen, nitrogen, fluorine, or chlorine, you can make hydrogen bonds. what part of this molecule is going to be partially negative? Where's the negative charge going to be on this molecule? It's a polar molecule. On the oxygen, why?
It has like 2 lone pairs.
It has 2 lone pairs, but even more importantly, it's the most electronegative spot on here. So it's the biggest blanket hog. It's the biggest bully. It takes the electrons and pulls them in close to itself. All right. If we're looking at the other force, if we have polar molecules that don't have a hydrogen directly attached to one of those big 4, we can still have these polar interactions, these dipole-dipole interactions. They're just not quite as strong. So we can look at 2 different similar compounds. This is the one that's on the slide right here for dipole-dipole attractions. Anytime you have these ball and stick models, black is almost always carbon, red is almost always oxygen, white's usually hydrogen. Occasionally, you can see the colors for hydrogen and carbon flipped, but that's pretty rare. Can this make hydrogen bonds? It has hydrogens in it, and it has oxygen in it. Can this form a hydrogen bond? No, why not? Because the hydrogen's not connected to the oxygen. So even though oxygen is still the big bully, it's still pulling the electron density towards itself. It doesn't have an easy target like hydrogen. Carbon's just a little bit more electronegative, and it has those core electrons to keep the nucleus shielded. So we will have a partial negative and a partial positive on this molecule, but it's not going to be as strong. Anybody know what this molecule is called? If anybody done any dissections in biology yet? Do they still do dissections in high school? I think we just did frogs. We didn't have to kill them ourselves. That was more of an ET thing. Everybody's seen ET, right? Okay. We didn't actually have to kill our own frogs, but we did have to cut them open, if I'm remembering properly. Maybe that was college. This is formaldehyde. This is what you use to preserve dissection specimens. If you take A&P at the college, you do a lot of dissections of different animals. You get to dissect a sheep's eyeball. And then they do, I think that they have different units where they say, okay, we're going to look at the pig's kidney today. And they just have a fridge full of all these preserved animal parts that they break out for these dissections. Yeah.
They almost outlined some like microbes. When I was doing the microbes after reach this summer, they've seen frozen and yellow formaldehyde. Teaching about the risk of significant signs of that.
They're moving away from using formaldehyde a little bit because it is slightly carcinogenic, and then there's different formulations of it. Basically, if you put formaldehyde in water, which is usually what you actually don't get formaldehyde. It reacts with the water molecule, and you get a molecule called formalin that looks like this instead. Similar formula. It's basically take formaldehyde and you add a water molecule to it, and you get formalin. This is actually doing the heavy work of doing the preservation in most of those specimens. So there are other aldehydes they can use. They tend to be not good for humans to breathe either. Most of my college students would have personal experience with this, perhaps. Formaldehyde's also what's responsible for the worst parts of a hangover, is because especially cheap alcohol tends to have small amounts of methanol in it. And when your body breaks down methanol, it actually makes formaldehyde. So if you drink cheap liquor, you actually are literally pickling your brain, because when your brain breaks down the methanol that's present in it, you make formaldehyde, and it's responsible for the worst headaches and there's a fuzzy feeling that's not strictly just a headache, but it's basically you can't think straight, which again, none of you would have any reason to have ever experienced before, but that's the result of the formaldehyde for the most part. All right. So if we have formaldehyde, it still has these attractive forces, these intermolecular forces, but they're not hydrogen bonds. Formalin is going to have a boiling point close to the boiling point of water. Formaldehyde has a boiling point that's about minus 20 Celsius. Very similar structures. The difference is the types of intermolecular forces that we have. Because the formalin can make these hydrogen bonds and the formaldehyde cannot, that's the difference between their boiling points. And so, and then last but not least is this category of these induced dipoles, these temporary dipoles. And those are our weakest intermolecular forces. Those London dispersion forces. And because those London dispersion forces, basically they're really weak. It's temporary polarizable molecules because you have something like a helium that has 2 electrons around it. Remember, this is the one where we said, okay, well, what if those 2 1s electrons both happen to be on the same side of the helium molecule at once? If that happens, it's not going to be very long-lived, right? Because these electrons are pushing away each other. They have the same charge. They can both be in the same orbital at the same time, but they're not still going to, in general, going to spend much time right next to each other because they have the same charge. If you wind up with a temporary situation like this, though, you do get a partial negative on the side of the molecule that has extra electrons and partial positive on the side of the molecule that's missing electrons. If this happens to be close to another helium molecule at the same time, it can basically pull the electrons to one side. So basically you got kind of this chain reaction where one molecule by random chance gets 2 electrons on the same side of it, which then if it happens to be in contact with another molecule at the same time, causes the same thing to happen here. Same thing can happen if you put it in the presence of a magnetic field. We can cause this to happen by putting things in a strong electrical or magnetic field. But these are going to be your weakest intermolecular forces. They're temporary charges. They still come from partial positives or attracted to partial negatives. And they're present in absolutely everything that has an electron. Is there anything that we've dealt with in this class that doesn't have electrons? Could make the argument that an H plus ion being moved from one place to another, you could say that an acid-base reaction has that H plus moving. But for the most part, almost everything we're going to deal with is going to have electrons, which means these dispersion forces are present in literally everything. They happen to be the weakest forces as well, but that's why everything has a liquid state, has a solid state at some temperature. It's because if you get things moving slow enough, even something like helium or something like a hydrogen molecule is going to have a little bit of intermolecular forces. All right, so how do I test you on this on an in-class test? Well, I can say something like, okay, you have calcium ions dissolved in water. What types of intermolecular forces are present and which ones are the strongest? And it's basically just a checklist, though, because these are the 4 types of intermolecular forces that we're going to deal with. That's it. I don't like to make absolute statements but I don't think that there's any category of intermolecular forces that's not on this page right here. Still hedging in my mind about whether or not I can say that because like I said, there's always exceptions somewhere, but I don't think so. In this case, I think all intermolecular forces fall into one of these four categories. Which means if I ask you a question like what types of intermolecular forces are present, you just go down this list. The first one's really easy. Does it have dispersion forces? Yes. How do we know? Because everything has dispersion forces. So on this part of the test, you can literally just go through. It's going to be three or four different systems, and you just have to say, okay, what's there and what's the strongest? And you can just go down the list and say, everything has dispersion forces, dispersion forces, dispersion forces. If it has anything else, though, that's going to be stronger. So if our system is NaCl dissolved in water, does it have dispersion forces? Yes. Does it have dipole-dipole attractions? It depends if you count hydrogen bonds as dipole-dipole. I kind of tend to favor saying these two are the same category of hydrogen bonds, just a specific category of dipole-dipole interactions. So that's actually one where both answers are correct. You could say, no, it only has hydrogen bonds, or you could say it has dipole-dipole attractions because it has hydrogen bonds, and they're both correct. So how do I grade that on the test? Leniently. As long as you're explaining your logic, then I can give you full credit for either of those answers. Typically, I try to make it a little bit more obvious. So you know what I'm asking for in this case. But it definitely has hydrogen bonds. Does it have ion dipole bonds? And how do we know? If we have NaCl dissolved in water, do we have ions? Yeah. And do we have dipoles? The water is a dipole, right? Any polar molecule is a dipole. So for this system, we have London dispersion forces. We have dipole-dipole because we have the water molecules interacting with each other. And more specifically, we have hydrogen bonds between the water molecules. Then do we have ion dipole? Yep. So what are the strongest forces that we have? Ion dipole, if you have them. Basically, the way to answer this question, what's the strongest intermolecular force present? It's always going to be what's furthest down on this list. If we looked at a different system, let's just look at, we'll use methanol again. Is that a polar molecule? How do we know? What's our criteria for polar molecules?
Symmetric.
We have to have a polar bonds, which means a difference in electronegativity between two of the atoms. So first criteria was we need polar bonds. which we said was a difference in electronegativity greater than 0.4. And then we also, in addition to having polar bonds, we also needed them to be pulling more towards one side than the other. Right? If we have 4 NFL teams playing tug of war that are all equally strong, nothing happens, right? So not only do we need polar bonds, we also need them arranged so that they're not exactly opposite of each other, which is what we called asymmetry. We have polar bonds here. I'll rephrase. We have 2 polar bonds here. Where are they? There's one polar bond. There's the other polar bond. And do we have asymmetry? How did we define asymmetry? One thing on a central atom is different than the rest. So we have a polar bond. If we're going to say what types of intermolecular forces are present, now that we have that drawn out, we just go down the list. Does it have dispersion forces? Yes, always. Do we have dipole-dipole bonds? Yeah. Do we have hydrogen bonds? We have a hydrogen directly attached to one of our big 4 electronegative elements, hydrogen to oxygen. Do we have ion dipole bonds? Do we have any ions present? If we just have methanol floating around, is that an ionic compound? It's not an ionic compound. We're not going to have ions floating around. So no ion dipole forces. You have to have an ionic compound to have ion dipole forces for now. And what's the strongest one? Strongest type of force we have present? Hydrogen bonds. Let's look at that formaldehyde one more time, just because I want to make one more point about is this a polar molecule? Do we have a polar bond? At least one. Carbon to oxygen is a polar bond, right? Do we have asymmetry?
Yes.
That's almost feels like a trick question because this looks like a really symmetrical molecule. It's nice and flat. You could draw a mirror down right in the middle of it. However, because this oxygen is not the same as these other 2, we do have asymmetry. We have the NFL team up here and we have our 2 Pee Wee football teams down here. So they're going to pull the electron density towards the oxygen. So we do have asymmetry, even though it looks like a nice symmetrical drawing. We're talking about asymmetry with respect to where the electrons are. What about if it was carbonate? This is a little bit trickier because it's an ion, but is it polar? Does it have polar bonds? Yeah, carbon to oxygen still, right? Does it have asymmetry? Why? Because they look different. They do, but they're all the same atom. Why are they different? So here's one of those confusing properties of electrons. How much time did y'all spend on quantum and orbitals? That was a while ago, right? Well, lucky for you, quantum in organic compounds happens to be my specialty. So we're going to revisit that for a second. Could I have switched which one of these has the extra bond? Is that just as stable? How did I pick where to draw the double bond versus only a single bond to the oxygens? I kind of chose it at random, right? Turns out electrons don't like to stay confined in one area. They spread out. They actually behave like what's called a probability function, a probability cloud. They exist everywhere in their orbitals simultaneously, which is weird to think about. Basically, what we get with a system like this, where we have 3 oxygens that are all equal, and we have to pick one of them to make a double bond, it's really more like each of them forms like a third of a double bond. So it actually turns out if they're all the same atom around that central carbon, it is actually symmetric. We have to pick one oxygen to draw to have a double bond, and the other 2 oxygens have single bonds, but really it's more like they take turns making a double bond. So a third of the time, this oxygen has a double bond. And even that's an oversimplification. It's more like those electrons are in all of those places simultaneously. So think about a fan blade. If you think just a regular fan that you would put in your room, keep you cool in the summer. If you turn that fan on, you can't see where the fan blade is anymore, right? It kind of is everywhere at the same time. It's a disc shape instead of just being a blade shape at that point, right? You wouldn't be able to stick your finger anywhere in there without getting it hit, right? Because even though that fan blade is really only one object, the way that it's moving makes it behave like it's one entire disc, or like airplane prop. Right? That whole thing is happening simultaneously. Electrons love to behave that way. Electrons don't like to be confined to any one spot, so they're everywhere simultaneously, which is weird. And why you should take Gen Chem, because we get to talk more about quantum in Gen Chem. You don't really have to understand it well until much later, but it is cool experiments you get to do. Remind me, nobody's taken physics, right? Unlike what, do you remember the name of the experiment that they used to show that light was a wave and a particle?
Yeah, that was.
They don't do that in axion physics. So
No double slit experiment.
We just slingshots.
All right, well, we'll leave that alone then for now. Paper airplanes are great though, but electrons are more fun.
We went to Six Flags.
Oh, you did that with Jake, with Dr. Rourke? All right. Here's some more practice problems. In this case, you said what types of forces are shown between the following molecules. If we have 2 nonpolar molecules, if it's a nonpolar molecule, what's the only type of force that it can have? The dispersion forces. I'll put the list back up here. Dipole, specialized form of dipole.
Yeah. Right, it's the same thing, yeah.
So if it's a nonpolar molecule, you don't have a dipole. If you don't have a dipole, you can't have dipole-dipole interactions. You can't have hydrogen bonds. You can't have ion dipole bonds. If it's a nonpolar molecule, the only type of intermolecular forces you can have are dispersion forces, those London dispersion forces. What about A? What type of bond is being shown in A? What type of intermolecular force is in A? Two polar molecules, there are dispersion forces as well. But if we have a hydrogen attached to a fluorine, that's definitely a polar molecule, and that fits that secondary criteria to make it be a hydrogen bond. So hydrogen fluoride will make hydrogen bonds, which is a subset of dipole-dipole bonds. What about C? C is really easy. You've got an ion forming with an intermolecular attractive force to a polar molecule, so it's ion dipole. You have to have an ion for that one to be present, so that one's really easy to recognize too. If there's an ion in a polar molecule, you've got ion dipole, usually along with the rest of them. And how about SO2? Can we have dispersion forces? Yep. Everything has dispersion forces. Do we have dipole-dipole? Sulfur attached to an oxygen, that looks a little bit different from what we've been looking at, but oxygen's one of our big four, right? So oxygen bonded to anything other than itself is going to be a polar bond. So we've got polar bonds. Do we have asymmetry? Well, if it's bent, we must.
Can you go over how you would want kids to remember like electronegativity values?
So in this case, the way that we're doing this right now without a table in front of you, basically, if you have a covalent bond that involves nitrogen, oxygen, fluorine, or chlorine, and anything else, we're going to call that a polar bond. The more specific answer is if you have a table of electronegativity values, like I'm going to give you on the final, we look for that difference in electronegativity of 0.4. So let me show you the exact table that you're going to be given.
Where are we looking for?
All right. So here's the periodic table that you're going to be given on the in-class test. And it has a list of electronegativity numbers built into this periodic table.
I do a read.
All right, so you're going to have to tip your head sideways because I don't know how to do this on a touchscreen in Dropbox instead of in a PDF editor. But we have sulfur and we have oxygen in this case, right? Sulfur's right there, 2.58. Oxygen's right above it, 3.44. Is that a polar bond? Yeah, we're looking for that threshold of, is the change in electronegativity greater than 0.4?
What do you use as your dividing line for ionic? Do you use 2.0?
For this class, I just say metal to a non-metal. Because it really is the criteria for, is it a pure covalent bond versus a polar covalent bond versus an ionic bond? It's really a spectrum. It's not as easy as it fits in this category. So there's a degree of how polar a bond can be. If you get to the most polar bonds, then you could start to call them ionic bonds. So typically for this class, I just say, if you have a bond between a metal and a non-metal, or a cation and an anion, it's ionic. When you get to Gen Chem, we can get more specific. Again, every time you take another chemistry class, we're gonna teach you how to be more specific and more writer. All right. Let me go back to so. Do we have asymmetry in SO2? What is the Lewis dot structure going to look like for SO2? How many valence electrons do we have for SO2? 6 electrons for each oxygen, and there's 2 of them. How many valence electrons for sulfur? Also 6 electrons. So we have 18 electrons total to work with. How many did we just use? 2 bonds. Each bond is 2 electrons. We used 4. 14 electrons left. How many does each oxygen still need? Each oxygen still needs to get to a total of 8 electrons, right? So we need 6 more.
No, you have 2.
We're down to 2 electrons left. Is that a good Lewis dot structure yet? What are we still missing? That sulfur is still missing a pair of electrons to be satisfied, right? So we make a double bond. That's an okay Lewis dot structure. It turns out there's a better one. I don't usually do examples in this class where we have to go past 8 electrons. So this would be a full credit answer for this class. And again, I keep saying this now, but we'll teach you why there's a better option when you get to Gen Chem.
So that goal there.
Yeah.
If you're going to be a STEM major in any capacity, you're going to take Gen Chem. At least half of it. Engineers get away taking only 1 semester of it, but only if you're doing the boring kinds of engineering. The cool engineering, you're going to need to take the whole year of it still. The cool engineering being chemical, biological, electrical, material science, where all the good stuff's happening these days. All right, back to the original question. Why did we draw this? So we can see stuff. What in particular? The asymmetry. Is this asymmetric? We've got lone pair, oxygen, oxygen. It's not 3 of the same thing around that sulfur, so we have asymmetry. So we have a polar molecule, we have polar bonds, and we have asymmetry, which means D is going to be dipole-dipole attraction. Fluorine is more electronegative. Is this dipole-dipole attraction too? Why not? Because it's symmetrical. It's bonded to itself. We don't have a polar bond if it's fluorine bonded to another fluorine. Right? Those are our NFL teams playing tug of war. All right. So why is this worth studying? Why do we care this much about the intermolecular forces? Because we can explain a lot of the physical world in terms of phase change and intermolecular forces. Intermolecular forces dictate how phase changes behave. When do they occur? What temperatures? Under what conditions? So because things like solids melting, liquids evaporating, gases turning into snowflakes in the upper atmosphere, those all affect our everyday life. Why is it that when you fry food, it tastes better than boiling food?
Because butter is delicious.
Because butter's delicious, and because as humans, as mammals, we have these hardwired tastes. Does anybody know what are there's three things that all humans in any culture learn to, or they love and want to eat more of: fat, carbs, so that's sugars, carbs, salt. All things that in a hunter-gatherer society you wouldn't be able to find on a regular basis. So we have this drive to eat as much fat, carbs, and salt as we can, because that's the way our species evolved. It's the way most mammals evolved. Most mammals love those same three things.
I don't.
You don't?
No, I just eat.
I don't know if you're lying or lucky.
Have you ever had deep fried Oreo?
I do like a good deep fried Oreo, although I like deep fried Milky Ways better.
Deep fried Oreos are so good. And fruit. Because I went to the market and I wrote this.
All right, bring it back. If something goes from a liquid to a gas, is the gas gonna have more intermolecular forces or less intermolecular forces? Both is an interesting answer. Somebody said less. Why?
You guess it. So they were actually there.
Yeah. If you have gas molecules, are there intermolecular forces between gas molecules? Usually. I mean, some, but only when they run into each other, right? Which doesn't happen that often. So in general, if you go from a liquid to a gas, we're reducing the amount of intermolecular forces. This is why you have to put energy into a liquid to get it to evaporate, to get it to boil. You have to add energy. You have to make those molecules move faster so that they can break apart from each other. Let's go back to cheap magnets on the refrigerator again. You have a bunch of cheap magnets on the refrigerator holding up a single piece of paper, each of them, so they're barely hanging on. If I picked up that refrigerator and shook it, what would happen? If the Hulk picked up the refrigerator and shook it, they'd fall off. Would all of them fall off? Probably not. Depends on how hard I shake it, right? The more energy you put into that system, the more likely you are to break some of those intermolecular forces. What if I had some of those really, really strong magnets on the front of the refrigerator and the Hulk picks it up and shakes it? The refrigerator is going to break probably before the magnet comes off. If it's one of those really strong rare earth magnets, right? The stronger the intermolecular forces, the harder you have to shake that system to get them to break those attractive bonds. Right? So the stronger intermolecular forces being present means we can expect a higher boiling point. Because it takes more energy to pull those molecules out of the liquid state and put them into the gas phase. And same with going from a solid to a liquid. If you have something, if we had water and it was really, really cold, let's say we had water at minus 40 Celsius, what state would we expect to find that water in? Frozen, right? A solid. As we add more energy, we get to the melting point. Now, does the liquid still have some intermolecular forces? Yeah, because everything's still pretty compact. Everything's still pretty tight. So those intermolecular forces are still going to hold those molecules together, but they're moving around a little bit more. You've broken some of the intermolecular forces, even though you haven't broken all of them yet. And to go from a liquid to a gas, you have to break all of those intermolecular forces. All right. Let's talk about statistics and how this all works with temperature. I'm not going to make you do the math. I'm not going to make you test for statistical significance. Basically, I mentioned the name Boltzmann the other day, and I said we're going to talk that he was kind of the founder of thermodynamics. Basically, what Boltzmann figured out was that if you have a system at a constant temperature, you don't really have all of those molecules moving the same speed. Temperature is proportional to the average kinetic energy of the molecules. But that's not saying that all of those molecules are moving the same speed at any given point. Right? Go back to my analogy with a bunch of ping pong balls in a moving box. If I shake the moving box, ping pong balls are all bouncing around. Are they all going the same speed? No, they can't be. Some of them are going to be rolling around on the bottom. Some of them are going to happen to bounce into each other just right and fly out of the top of the box. All we're really looking at with temperature is what's the average speed of all the molecules in there. And as you add more energy to the system, the average speed of the molecules goes up. Right? And that's what this shape is showing. This shape is called a Boltzmann distribution, which is sort of like a version of a bell curve that's more useful in physics. The Boltzmann distribution basically says, okay, at a certain temperature, the distribution of how fast your molecules are going or what their kinetic energy is going to have this overall shape. It looks kind of like a bell curve, but it's not truly a bell curve. Because what happens when you get down here? Can you have, if it was a true bell curve, what would it look like? If we had energy, kinetic energy here, and fraction of molecules here. If it was a true bell curve, say that this is the average. Bell curves are symmetrical, right? Unless they're skewed, but let's ignore that. True bell curves are symmetrical, which means what happens down here when you get to zero? This would actually say if it was a true bell curve, that would be saying we could have molecules with less energy than zero. Can that happen? If we're at zero kinetic energy, that would be being at 0 Kelvin. We can't actually get colder than 0 Kelvin, right? So they needed a new type of function to describe the way these molecules move. That's what the Boltzmann distribution shows. Basically, the colder you get, the more this function kind of scoots over to the left, the narrower it gets, but it doesn't shift the whole thing over because you can't go below 0. All right. What does that mean Why am I showing you this if I'm not going to make you do any of this math? Basically, as you get to higher and higher temperatures, if we go the other way, higher temperatures means this whole shape spreads out more, moves more to the right, gets lower. You have a higher range where you're likely to find these molecules. Any chemical process, any reaction or phase change basically has a threshold you have to get above for the reaction to happen. So go back to the ping pong balls in the moving box. Let's say that the phase change, evaporation of those molecules, means a ping pong ball bounces out of the top completely. If I shake it really gently, are any of those ping pong balls going to jump out of the top? Be very, very unlikely. If I did it long enough, then maybe given enough time, like the lifespan of the universe, maybe one of them would happen to bounce out of the top. But the average molecule, ping pong ball, is not going to have enough energy to make it over that threshold. As I start shaking the box higher, as I give it more and more energy, this function flattens out and moves more to the right. As soon as the average energy is above that threshold, that's when you start to see a measurable phase change. Right, so phase change happens when most of our molecules can get out of the box. If I shook that moving box as hard as I could, all the ping pong balls are going to fly out of it, right? So that cutoff, how high the box is really going to dictate how much energy, how hard do I need to shake the box in order for it to happen. Right, and so this is why even if you never get to 100 Celsius, you have a water bottle, you leave the top off your water bottle and you leave it in your car for a month. Is there going to be any water in it when you come back? No, what happens to it? But it never got above 100 Celsius. It didn't boil, so how could it go through a phase change? Because some of the molecules did have enough energy to make it out. Some of the molecules at random happened to bounce into each other just right so that one of them flew off into the gas phase. Right? So there's actually always small amount of what we call vapor pressure above a liquid, because some of those molecules are going to have enough energy to escape. Does that happen faster or slower if you leave your water bottle in the car in the summer? Faster, because that shape is a little bit wider. A larger percentage at a higher temperature, the red line here, a higher percentage of the molecules can get over that threshold, that cutoff. Right? The hotter it gets, the more of your molecules can do that. And what happens if you leave the cap on to your water bottle? Does the water ever fully escape then? Some of the water molecules escape the surface, but then they're still stuck inside the water bottle bouncing around. And what happens when one of those water molecules bounces off of the lid and then back into the surface? It's going to kind of get like reabsorbed, right? Right, so these water molecules, you're going to reach sort of a standard vapor pressure for a given temperature, where you have a certain percentage of your molecules are found in the gas phase, and the rest stay in the liquid phase. All right. Let's talk more about phase change. I think I have a figure like this already. We talked about it. We defined some of these terms. If you have a liquid and it goes to a gas, we can call that evaporation, or we can call that vaporization. They mean the same thing. what happens if you have a cold drink in a humid environment? What happens to the outside of the can? Condensation. The gas condenses or condensates on the outside of your can. So anytime you go from a gas to a liquid, that's called condensation. It's not just water that condenses. You go from a solid to a liquid, that's melting. If you go from a liquid to a solid, that's freezing. Regardless of what the liquid is, which sounds weird, but bacon fat congealing, turning into a solid when you're done cooking, technically that's bacon grease freezing. The more scientific way of describing that is you could call it solidifying. We call that process fusion, right? So when we talked about energy, we defined that. We said that there was a certain amount of energy associated with phase change. And the energy associated with going from a liquid to a solid, we called that fusion. So fusion, freezing, solidifying are all valid ways to describe that process. Because we're used to thinking about water as the only thing that freezes, it sounds a little bit weird to say that anything else melted iron solidifying could be called freezing. If you go into planetary sciences, if you go into astronomy, they call pretty much everything an ice, which is weird to me. But they say that you could have, if you had solid hydrogen, they would call it hydrogen ice. Don't ask me why or where that comes from because I'm not an astronomer, but that's apparently a thing. Then the last two that we have less experience with, we talked about it before though. Sublimation is going straight from a solid to a gas. Deposition is going from a gas to a solid. How many of you drive in the morning and have been noticing the ice on your car in the last few mornings, last week, 2 weeks? Does it look like frost or does it look like ice? And what's the difference? It's been kind of weird. Our weather's been weird here lately with all the fog, right? It's kind of in between. It doesn't really look like frost though. Not like the frost we're used to seeing. Frost is a good example of deposition. Really, what I think we've been seeing on our cars the last couple of weeks is condensation followed by freezing. So we get dew forming on our cars that then freezes, which is why it looks different than the really sharp crystalline shapes we see when it's a true deposition process. So how do we know which of these processes something will go through? Why is it the last few weeks we've been seeing deposition or we've been seeing condensation followed by freezing instead of deposition? It turns out we can describe the conditions for phase change are going to be based on two variables. What's the most obvious variable that's going to control phase change? What do you usually think about doing? If I told you, here's a piece of ice, I want you to make it go through a phase change, what would you do? Heat it up. So temperature is the most obvious variable for controlling these. Living up here in the mountains, we actually have some experience with the other variable. Make sure I get these axes properly. Yeah. Temperatures on the x-axis. What's different about being at altitude compared to sea level? What changes how we cook? Pressure. Being in the mountains in general. So this is what's called a phase diagram. A phase diagram basically looks at different conditions. It looks at your pressure and your temperature. And then we basically draw lines on it to show where we get phase changes happening. They're always going to have the same general shape. If we're at really low temperatures and really high pressures, what phase would we expect to see mostly? like really high pressures, really low temperatures. What phase? Solid, liquid, gas? Solid. Without even filling anything in here, we can expect that we're likely to find solids at low temperatures or at high pressures. What about high temperatures, low pressures? What phase? High temperature, low pressure. It's going to be a gas. And then what's in between the two? Liquids. So the general shape of a phase diagram is going to be kind of like a curved line. It doesn't need to be too specific. That's going to differentiate between solids and gases. And then if the conditions are right, you can see a liquid. So this overall shape of a phase diagram is going to be the way we can describe what types of phases we can have at different conditions. Right? And so this line, let me draw it a little bit more carefully, basically goes up off the graph here. This line has basically, there's a point at the end where it basically stops. If we get to really high temperatures, we would expect pretty much anything at a high enough temperature to turn into a gas, right? But if you add enough pressure to it, you can actually get this state where it's kind of behaves like it's a gas and a liquid at the same time. Does anybody have a guess what that's called? Usually somebody's heard of, like, well, isn't there a fourth state? I've heard of it. Nobody? Plasma. Plasmas do overlap with a lot of these. That's the answer I'm used to hearing. So thank you for humoring me. We actually call this a supercritical fluid because plasma has a very specific definition. Plasma means basically that your electrons have so much kinetic energy that they don't stay attached to the nucleus anymore. Basically, if you have a plasma, you have nuclei and you have electrons, but they're all just sort of freely moving around. Supercritical fluid's not quite to that level yet. It's getting there. All plasmas are supercritical fluids, not all supercritical fluids are plasmas. So this point right here, why do we call it supercritical fluid? Because that's called the critical point. The critical point is a set of coordinates, is a temperature and a pressure, where if you get above that, you can't tell the difference between a liquid and a gas anymore. Gases already behave kind of like liquids. It's basically, you could think of it, supercritical fluid as being a gas that's so condensed, where there's so much pressure that you're forcing your gas molecules to be close like a liquid, even though they have enough energy to be a gas. So go back to our ping pong balls in a moving box. If I put a lid on the moving box, it doesn't matter how hard I shake that box. The ping pong balls are stuck there, right? They can never get out of that box to become a gas, no matter how hard I shake it. So we're keeping it as kind of a liquid, even though it has enough energy to be a gas. All right, why is this useful? Why don't we have a picture like this if we talk about the boiling point of water? What's the boiling point of water in Celsius? 100 Celsius. What's the freezing point of water? 0 Celsius. Always?